Good afternoon. My name is Jing Wang. I'm from the Human Health and Performance Systems Group at MIT Lincoln Lab. For this presentation, I'd like to tell you about our group's work on using vocal biomarkers to automate the screening process for post-traumatic stress disorder. But before I dive into this topic, I'd like to first tell you about another exciting project our group is starting. As we have heard many times today at the symposium, women's health and performances is an under-researched topic by the academic and scientific community. There are significant knowledge gaps in how to best serve our military women as more women seek combat arms and special operations assignments. MIT Lincoln Lab has taken notice of this gap as well. Our technology office has decided to fund a survey study to identify gap-filling technologies Lincoln Lab can develop to address some of these standing issues. The study team consists of Lieutenant Colonel Kristen DeWild-Schroeder, as we know, Brian Baum, and me. We decided to focus on the 4 areas shown on the slide here. In the interest of time, I can't go in depth here, but if you would like to hear more about the study, or if you have valuable information for us, please come to talk to us during the breaks. We would love to hear from you. The focus of today's talk is on using vocal biomarkers to screen for PTSD. This is the one example technology that's developed here at Lincoln Lab that we have identified to have a high potential to be extended to address some of the standing behavioral health problems, issues faced by military women today. So PTSD is a widely prevalent health problem faced by military service members in general. According to a 2020 survey, since the September 11 attack, 83% of U.S. service members have reported experiencing some form of PTSD as a result of their military service. The statistics in the red box here shows that in recent years, there were more service members died by suicide than combat. The plot on the bottom right here shows the incidence rate of PTSD in active duty military service members. It's broken down by gender. The dotted lines are female. The solid line is for male. As the plot shows that since 2009, while the incidence rates for male have more or less tapered, it's still increasing steadily for female. While there are many possible explanations behind why we're observing this phenomenon, it highlights a need for an efficient PTSD screening tool to ensure all of our service members, both men and women, can get the counseling and treatment in a timely manner. So PTSD screening today is typically done via self-report surveys and then further diagnosed via clinician interviews. There are a few challenges with this approach. For example, some patients may not be self-aware enough to accurately answer these self-report surveys. Some patients may have comorbid conditions such as traumatic brain injury or depression, which may cloud their judgments and prevent them from accurately answering these survey questions. Another challenge is the stigma and perceived career impact. Some patients may purposely try to game these survey answers to avoid the PTSD label. Another challenge is infrequent screening. Typically today, PTSD screening is done during the annual health assessment via online surveys or interviews, unless it's otherwise scheduled due to deployment or their being in the special force. Our goal is to leverage an objective, automated screening tool that can be administered more frequently as part of regular medical visits to ensure early diagnosis and treatment. As we know, early detection and identification of patients at risk of PTSD allowed their therapists to take advantage of the golden time window for treatment. Early treatment improves the treatment efficacy and also reduces recovery time, as studies have shown. So one automated method that has shown promise in detecting signs of affective disorders is voice analysis using vocal biomarkers. A vocal biomarker is a measurable characteristic in the speech signal that enables insight about physical or mental state by capturing changes in sensory, motor, and cognitive function. When we speak, it's not the simple movement of our mouth, but rather it's a result of many neurological pathways working in concert. Example neural pathways include auditory perception, sensory motor coordination, and emotion regulation. We often express our emotions through speech. The limbic system is known to be involved for regulating our emotions. It is hypothesized that the limbic system is affected by PTSD, so this in turn may lead to a difference in speech production between patients with PTSD and the healthy population. Over the past 13 years, our group at the Lincoln Lab have developed a wide range of vocal biomarkers to capture subtle changes in your voice. We grouped the vocal biomarkers into 3 categories based on the vocalization anatomy, as shown by the figure to the right here. The 3 main vocalization subsystems are articulation, phonation, and respiration. An example vocal biomarker for the respiration subsystem is the envelope of your audio or voice signal. It roughly translates to the modulation in the volume or loudness in how you speak. An example vocal biomarker for the phonation subsystem is pitch, which is the vibration frequency of our vocal folds. We have several vocal biomarkers to capture the articulation subsystem. One set of vocal biomarkers for that is the movement trajectories of our articulators. Here's an MRI video of someone speaking. We took the soundtrack of that person's voice and back calculate the movement trajectory of various articulators, such as the position of the tongue or the degree of protrusion of your lip. That's the time series you are seeing here to the plot to the right. And this is the MRI of someone speaking. You can see the tongue tip is here, and the lips position is here. It's hard to see when the video is moving, but I will take a frozen still frame here. If you pay attention to the tip of the tongue here, which is calculated by the plot, second from the bottom right plot here, the value of this variable is pretty low when the tongue is at its resting position. When the tongue tip moved to the alveolar ridge right behind upper front teeth, you can see that the estimated position for the tongue is at near its peak. So these time series variables is what we call vocal biomarkers. Here is the processing pipeline for our algorithm. For a given voice recording, we first assess the signal quality. If there's noise, such as room reverberation in this recording, we first try to improve the signal quality. This is an active area of research we're currently working on. If the signal is deemed of sufficient quality, we then compute the low-level vocal biomarker features, such as the time series you've seen in the earlier slide. We then feed these vocal biomarker features through an emotion estimation algorithm to get estimate of the emotional states throughout the entire recording. Based on emotional states of the voice, we select segments of speech that can provide more salient characteristics for PTSD detection. For the selected segments of speech, we then compute higher level statistics to formulate what we call high-level vocal biomarker features. These features are then fed into a machine learning algorithm, which will then produce a likelihood score for PTSD. What's unique about our approach is this use of emotion estimation algorithm and emotion filtering. The emotion estimation algorithm was a result of earlier work led by Yosarium and sponsored by MMRP. This emotion estimation algorithm uses a 2D emotional space. The 2 axes are arousal and valence. Valence is referred to how pleasant or unpleasant you'll feel, and arousal is referred to level of alertness. It can vary from feeling calm, like low arousal, to feeling really excited. For PTSD detection, we're primarily interested in 2 quadrants on this 2D space. First is the high arousal negative valence space, which correspond to emotions such as anger and frustration. We know many patients with PTSD experience hypervigilance and high sense of insecurity and fear of their safety about their surroundings. Another quadrant we're interested in is, I will exit. I will let you work out at the background. Another quadrant we're interested in is the positive valence lower arousal state, which correspond to emotions such as feeling calm and content. we know that some studies have shown patients with PTSD have a difficult time experiencing emotions in this emotional state. So we hypothesize that if we look for speech segments that correspond to this lower arousal positive valence state, we will have a better likelihood of identifying speech segment differences between healthy subjects and the PTSD patients. So to test our hypothesis, we ran the algorithm with different emotional filtering settings. The result of our algorithm is shown on the right plot here. Along the x-axis is the probability of false alarm, and along the y-axis is the probability of detection. The diagonal dotted green line shows the probability of a classifier giving classification results by chance, simply guessing. It has a area under curve of 0.5 or 50-50 chance getting correct. Ideally, we would like our classifier to perform towards the top left corner that has a low probability of false alarm and a high probability of detection. So if we do not use any emotion filtering, we can achieve area under curve as shown by the yellow plot here. It has area under curve 0.68. If we use emotion filtering to select for segments of speech correspond to emotions such as fear and anger, we get a small improvement of area under curve to 0.7 as shown by the red plot here. But if we look for speech segments corresponding to relaxed, calmed states, we get a bigger boost in performance to 0.8 as shown by the blue plot here. So achieving an area under curve of 0.8 is important for us because that is at a breaking point at which a machine learning algorithm can be considered clinically relevant. So our preliminary results here show that there is promise in using this emotion filtering approach to improve the detectability of PTSD using vocal biomarkers. We're also hopeful that we could extend this methodology to detect other types of affective disorders such as depression. Here's how we envision we would like to use the algorithm in operation. When a patient comes to the clinic, we can hand them a recording device to record their voice. This data will be analyzed in near real time, and the results will be sent to a clinician who can then make a more informed decision on whether or not a further mental health investigation is needed for this patient. Using our current prototype, this whole process takes about 4 minutes to complete. Here's the summary of the data sets we've used to train and test our algorithm. We first trained the model using recordings from the sound booth for pristine signal quality. This will maximize our chance of identifying subtle voicing differences between patients with PTSD and the healthy population. We then tested our algorithm on more realistic environments, such as quiet offices and noisy clinics, as shown by the 2 columns on the right here. What I would like to draw your attention to is the number of female subjects in all 3 data sets. We acknowledge that there is gender imbalance in our training and test data. We are actively working on networking with the different clinical institutions to expand our female vocal sample representation in our database to reduce the bias in our model. Currently, without sufficient female vocal samples, it's hard to say how well our algorithm will work for the female population specifically. So in the future, once we have sufficient data, we would like to build gender-specific models to improve applicability and generalizability of our algorithm. In summary, as you recall from our earlier slide, that 83% of U.S. service members report experiencing some form of PTSD. We really hope that vocal biomarkers could be a part of this solution. Our initial results show that there is promise in using vocal biomarkers to screen for PTSD. We are currently working on expanding our data set to include larger and more diverse population to reduce the bias in our model. We are also actively working on iterating the screening tool prototype design and working with the clinicians to generate a more informative user interface. One of our goals is to work with clinicians to hash out the CONOP and also to understand gender and sex-specific symptomology and any index trauma differences that could improve our algorithm general applicability for all military population. We have published our work in the paper shown here. If anyone's interested, then you can take a read there or come and talk to us after this. I would like to acknowledge our sponsor and the collaborators on this work. Lastly, I would like to put the plug back to the survey study that Lincoln Labs Technology Office is funding. We would like to identify gap-filling technologies that Lincoln can develop to address some of these standing issues. So if you have any inputs for us, here's our contact, and please come talk to us after talk. Thank you.